Hey, welcome back to the party. Now that we've taken a look at some of the Jello, right? I got some Jello blocks that we can have. So any good fraternity knows that Jello blocks are where it's at. I've even made a few for you, and we're hoping that from these Jello blocks we can learn a little bit about defining Poisson's ratio for engineering materials. So that was our next learning objective there. So I want to take one of these blocks and I want to just figure out what is Poisson's ratio. So I have this Jello block. It smells delicious. And strawberry. And if we think about it, when I put a load right onto a surface of this block, what do you think is going to happen? If you're not sure, I recommend you go to your cupboard and mix up some Jello now to get in the spirit. As we push down, hopefully you can see that in there. As we push down, the Jello block tends to bulge outward, right? So hopefully we see that sort of bulging action. As I apply a vertical load here, it bulges outward in both directions. Now this is kind of back to the idea that matter, right, can't be created or destroyed. So if I compress the top, because I'm compressing the material, some of that material is pushing out, and it's going to push out this direction and this direction. And in engineering, we are interested in knowing, depending upon the applied force, how much is it going to bulge out on either sides? Or if I have a longitudinal force or longitudinal strain, what kind of lateral strain or lateral deflection, right? Longitudinal compression leads to lateral expansion, in this case for the Jello block, right? But we saw Poisson's ratio doesn't just have to apply to Jello. It's very easy to see in Jello, but it applies to our metals too. When we had Stelio, as we pulled him towards failure, he began to neck, right? So that action of necking, we were pulling in the longitudinal direction, but shrinking in the lateral direction. All right, so that's basically what Poisson's ratio is. So let's go ahead and jot that down into our notes real quick. So Poisson's ratio is the ratio of lateral strain to longitudinal strain. And if we go back to mathematics, we know that a ratio is simply a fraction. So our formula for Poisson's ratio is going to be the lateral strain divided by the longitudinal strain. To help us remember what Poisson's ratio is from a physical standpoint, I just want you to recall the bulging of this Jello piece, or you can recall the necking of Stelio. So both of those are examples. Poisson's ratio will be represented by the Greek letter nu, that is Nu. And the Greek letter nu looks like a little V, but it's kind of got like a little curly V aspect to it. I draw it as such. You'll see it's kind of like a V, and then it has a little bit of a curl to it. And it's equal to the fraction, and it's going to have a negative sign in there. Remember, Poisson's ratio is a ratio, and it's a positive number because we'll assume that if the longitudinal strain is compression, then the lateral strain will be tension. And so we need to have that negative just so we can get one value for the ratio. Finally, we note that for all materials, Poisson's ratio needs to be between 0 and 0.5. 0 represents a material that is, basically unmoving no matter how much force you put on it. It does not expand in the lateral direction, whereas 0.5 would be material kind of close to Jello, where you have almost as much movement as you have in the vertical direction as how much movement you have in the lateral direction. We can't really go above 0.5. If you go above 0.5, that means that your object, as you're like squeezing it, it's like magically multiplying or growing in the lateral direction. So that's why we have that bound on Poisson's ratio. For most engineering materials like aluminum or steel, our Poisson's ratio will somewhere be between 0.25 and 0.33. Something a little bit less movable like concrete, you're down in the 0.1 to 0.2 vicinity. All right, peeps. Jello blocks aren't just good for Poisson's ratio, they also are good to tell us a little bit about the shear stress and shear strain behavior, right? So if we have an initial block and say I set it up so that this is my y-axis and this is my x-axis, I want to look at what happens if I apply a shear to this block. So a shear would be on this surface, and I'll apply it to the right, and also on this surface, and I'll apply it upward. So imagine I was doing both of those at once. Oh, I think you could see something like that would happen. We get kind of a skewing of the block. I'm just going to do the one so you can see it obviously. You get kind of like this parallelogram action, right? So anytime we see kind of that skewing, if we had a rectangle and then after applying load, if we had like a parallelogram, you usually can infer that shear deformations have occurred or some sort of shear stress is present in the material. Okay, so I want to come up with a relationship for the shear stress versus the angle of deformation. We're going to use our axial stress strain behavior to help kind of correlate and come up with this relationship. All right, catch you in a few. So similar to axial behavior, we can examine the behavior of an element in shear. So I want to examine that Jello block, and I want to draw the initial Jello block, and I'll draw that here as a black square in a 2 dimensions. So in my XY plane, I have this black square. Now I took my Jello block and I applied a shear force or shear stress to the surface. The shear stress will be denoted by the Greek variable tau. So it's a little curly T. So I said I applied a shear stress, so that was going to be a stress that was in the plane on top of the Jello block, but then like sliding in the X direction. And when we applied this force in our physical model, we saw that it became like a parallelogram. It tended to kind of skew the block sideways and upward a little bit. And so this was the final shape drawn here in dark green. So we have the displaced shape of the block, and we can measure just like we did in axial stress, right? And we had axial stress, and then when we had axial displacement, we looked at axial strain. When we look at shear stress, because we get this skewing, we're going to look at shear strain as an angle. So shear strain will become this angle between the skewed element and the x-axis. So our variable for shear strain will be gamma. In this case, it's gamma xy because it's in the xy plane. And likewise on the vertical surface, we also have a gamma. And so the combined skewing, if I apply a unit shear to this block, I get an angle on the bottom and an angle relative to the vertical. And so when I add those two together, gamma over 2 plus gamma over 2 gives me gamma. And now I'll want to look at my shear stress versus shear strain behavior, tau versus gamma. Now, we haven't really talked too much about shear stress, and we're going to get more into this when we talk about torsion. But we'll see that shear doesn't behave quite like axial stress and strain. It's similar in the sense that it has a linear elastic region, but doesn't really show the yield plateau. It basically goes from linear elastic to some sort of strain hardening curve and then ultimately fracture. We do have that linear elastic portion, and so in the linear elastic range for shear stress and shear strain, we can set up a relationship that's basically tau equals g gamma, where g is our modulus of a rigidity. And so g is kind of the same thing as modulus of elasticity E, or Young's modulus. It's kind of the analog to that for shear stress and shear strain. Again, I just wanted you to note that there was no yield plateau. So when we talk about shear stress and shear strain, we really want to be in the linear elastic range. Otherwise, we're really going to have to kind of model the full material behavior. Finally, I just want to write down the formula for G. G is going to be tau divided by gamma. But as it happens, this is also related to the modulus of elasticity through Poissons ratio. So we see that there is a relationship between axial behavior and shear behavior, and it somewhat depends on Poissons ratio for the element. All right, let's get back to more fun with Jello blocks. All right, I hear the DJ playing the music. I gotta get going to the party. Hope you join me with having some of these Jello blocks.